Welcome to lesson 3.3. Today we'll be graphing an inequality in two variables. Our objectives are to draw boundary lines, to graph inequalities in two variables, and to locate the solution area. Just to remind you, these are some of our inequalities. We have a less than or equal to, a greater than or equal to, and then just a less than or a greater than. And this is going to be important when we draw our boundary line to know which one we are using and how that affects the line. So here we have some essential questions. You might want to write these down if you're taking notes. These are good questions to be able to answer. So number one, what is a boundary line? A boundary line is a line that separates the coordinate plane into two. Whenever you graph a function, essentially you are graphing a boundary line. What is the difference between graphing an equation or graphing an inequality? And really, the difference, except for the style of line. You either do a dashed or a solid line, and then there'll be some shading of our solution area. When you have an inequality, you have a number of solutions, versus when you graph an equation, your solutions are only the points that are on the line. And then our final question is, when do we use a solid line for the boundary as compared to a dashed line? And this is where the inequality sign is important. A solid line is used when the inequality sign has an equal to on the bottom. So a less than or equal to, or a greater than or equal to. That line on the bottom means go ahead and use a solid line because all the points on the line are then part of our solution. A dashed line is used when the inequality is just a less than or a greater than. And the reason we then use a dashed line is because any of the points that are on that dashed line are not considered solutions in our solution area. Okay, let's try some examples. So here in our first example, this linear inequality is written in slope-intercept form. So I can quickly identify that here, the 2/3, that is our slope. And then the 5, that is our y-intercept. And that's how we can graph this. So this is our y-intercept. So very easy to graph. All I have to do is plot my y-intercept down here at -5, and then I'm going to use my slope in order to plot the next point. So we have rise over run. We have a rise of 2 up 2 and a run of 3. 1, 2, 3, and I plot my next point. I only need 2 points to make a line, so I can be done here, or I can do a third one if I need it to be more precise. The last thing I'm going to check is the slope itself. I have a positive slope, so I want my line to increase as I move from left to right. So now I'm ready to draw my line. And I just need to think to myself, is this going to be a solid line or is it going to be a dashed line? Because it's a less than or equal to, remember that or equal to on the bottom, it means that I will be drawing a solid line through my 2 points. Okay, and again, this is a boundary line separating the coordinate plane into 2 equal parts. Well, not necessarily equal, but 2 parts. Now let's figure out where to shade. So what this is saying, the inequality is saying I want to shade all the y values that are less than or equal to the boundary line, right? This is my boundary line, this 2/3 x minus 5. Well, less than or equal to this line is going to be below the line down here. So all the points down here, including the points on the line, are all going to be solutions to this equation. Okay, let's try this second one. In the second problem, I don't have y equals mx plus b. It's not quite in slope-intercept form. It's close, but it's not exactly. So what I need to do in order to put it in slope-intercept form is get rid of this 4. So I just need to divide all terms by 4, just like this. And then let's write what we have. So for my final equation, 4 divided by 4 is 1, which leaves 1y. Is less than, I can't divide -5 by 4 and have it come out evenly, so I'll just leave it as -5 over 4x plus 16 divided by 4 is 4. Now I'm ready to graph this. So my y-intercept is up here at 4, and my slope, notice, is -5 over 4. I have a negative slope. So it doesn't matter if I go up or down, but then I just have to be careful which way I go, left or right. So let's go ahead and go down 5, 1, 2, 3, 4, 5. Then I'm going to want to go to the right 4, 1, 2, 3, 4, in order to ensure that my line slopes downwards from left to right in the negative sloping direction. All right, now I just need to draw my line. So again, I need to make sure that I am using a dashed line because it's just a less than and not a less than or equal to. So my boundary line is dashed. Finally, when you're graphing, we just need to shade. This equation or inequality says I want to shade all the y's that are less than the boundary line. Well, down here, the y's are less than the boundary line, so I would shade down below. All right. These points down here where I've shaded are all going to be solutions to this inequality. I could take any point, plug it in this equality, and it would be true. The left side would be less than the right side. Okay, let's try another example and then we'll test some of our points as we move forward. In this example, we definitely don't have it in slope-intercept form, so we need to rewrite it. First thing is I need to move the x to the other side, right? Because it's y equals mx plus b. So I would move this over. This is a positive 9x, so I would need to subtract it from both sides. All right, so when I do that, what I'm left with on the left side is just the 3y, and it's greater than negative 9x minus 6. Finally, I need to get rid of the 3, so I would need to divide every term by 3. 3 divided by 3 is 1, or 1y, which is less than negative 9 divided by 3 is negative 3, x minus 2. And this is the equation that I'm going to graph. This is the equation that I'm going to use to help me know where to shade as well. So, first things first, let's go ahead and plot our point. So our point is going to be at negative 2, our y-intercept, I should say. And our slope is negative 3 over 1, right? If it's not over anything, it's over 1. So I'm going to go up 1, 2, 3, but then I need to go to the left 1 in order to ensure that my line is sloping in the negative direction from left to right. All right, so we are ready to draw our boundary line, and we just need to determine that our boundary line, in this example, is going to be dashed because we just have a greater than sign and not a greater than or equal to sign. Let's look at our shading. So we want all the y's, we want to shade all the y's that are greater than our boundary line. Well, our y's that are greater are above right here, so I'm going to shade above. So now that we've had some experience graphing and shading, I want to show you how to test points. So let's pick a point in our shaded area. Let's pick a point like 0, 0, because that's a very easy point to do math with. So let's do a test. So I'm going to test 0, 0. And if 0, 0 is in my solution area, then it should be true when I plug it in. So let's try it. I can plug it into my original equation, or I can plug it into my new equation. I think I'll go ahead and plug it into my original equation. I think that will be a little bit easier. So I replaced the x with 0, and I replaced the y with 0, and now I'm going to simplify. 9 times 0 is 0, plus 3 times 0 is 0. That leaves 0 on the left side, and 0 needs to be greater than negative 6. Is that true? And it is true. 0 is in fact greater than negative 6. All right, and that's how you test to see if a point is in fact true. We'll try that on the last one as well. All right, our final example. Again, we have a problem that is not in slope-intercept form, but we know how to convert that. We would need to move the x to the other side by subtracting it. And we are left with 3y is greater than or equal to negative x plus 18. Finally, I would just want to divide by 3, divide each term by 3 in order to isolate y. 3 divided by 3 is 1, or 1y, is greater than or equal to, and this right here is a negative 1x over 3. So this is the same as negative 1/3 third x plus 6. 18 divided by 3 is 6. Okay, plotting this, let's plot our first point here at the y-intercept. Our slope is again negative. It's negative 1 over 3. So I'm going to go down 1 and over 1, 2, 3. When I look at my inequality sign, I can see that I have a greater than or equal to. So in this case, I need a solid line. So I'm going to go ahead and graph a solid boundary line. I'm going to adjust that just a little bit. And we'll adjust this up. And then I just need to shade in the right location. So the problem says I need to shade all the y's that are greater than or equal to this boundary line. Well, that would be above the boundary line, so I would need to shade all the y's up here. Now let's go ahead and do a test point on this one. Unfortunately, 0, 0 is not in our solution area. I could still use it, but then I know that I would be getting a false statement. So what instead I want to do is pick a point, though, that's in my solution area and test that. So let's test a point up here. And I know that I could test a point on the line as well because that should be a solution. But let's go ahead and test this point for 10. How about way up here? So let's test 4, comma 10. And if I plug it into my original one, it should be greater than or equal to 18. So let's try that. Let's replace the x with the 4, and let's replace the y with the 10, and make sure that it's greater than or equal to 18. Well, this gets me 4 plus 30, and I'm pretty sure that 4 plus 30, which is 34, is in fact greater than or equal to 18. This is a true statement, and that test point is accurate, which means I shaded in the correct location. All right, and that concludes our lesson for today on graphing linear inequalities. So at the end of this lesson now, you can draw boundary lines. You can graph an inequality in 2 variables by switching to slope-intercept form, and you can locate and shade the solution area.